Okay, so we're going to talk about a decay model, and we're going to talk about a half-life, and I believe we've talked about this before. We're going to go back to our model, A equals A naught e to the kt. Okay, and a half-life is how long it takes something like a radioactive material to decay to half the amount. Okay, so this time we're not doubling the amounts, but rather we're cutting it in half over a period of time. So a half-life is how long it takes for some decaying thing, some decaying material, usually it's a radioactive substance, to decay to half the amount. Okay. So we're going to go through this example. The book goes through and shows you a formula, but then they don't use it. So I'm just going to show you the example here and explain it. And I'll tell you, if you're following along in the book, there are some typos. Too many for me to kind of point out, but you'll see them. Anyway, here we go. So the half-life of carbon-14 is 5,730 years. So that is going to be our time. We're going to think about that amount of time in our model. So we're going to start out with our model. And then we're going to say, well, we don't know how much money we're starting with, or how much money, how much substance we're starting. We don't know the amount of what we're starting with. But we do know that after this 5,730 years, we're only going to have half of it left. Okay, so we set up our formula that way. It doesn't matter how much we start with, 1,000 grams, 200 grams. It doesn't matter, because over that period of time, we're only going to have half of the amount left. Well, this creates this formula then. We can divide both sides by A naught, which is very convenient, very handy. And so we get 1/2 equals A to the, let me write this as 5,730K. Now, you might be saying, well, what are we trying to do? We're trying to express the amount of carbon-14 remaining as a function of time, so we need to solve for K. That's what we need to do. Okay, so we're going to do two things. One, I'm going to change this to 0.5. It's a little bit easier to write. And then I'm going to take the natural log of both sides. I'm going to natural log it. That's what we've been working on, solving these equations. And so we use that property, that logarithmic property that says when the base in the argument matches the base of the logarithm, then it just equals the exponent. Okay, and then we can just solve for K by dividing by 5,730. Okay, now this is the exact value of K. They talk about using an exact value. So in our formula, how do we write that? We can write A equals, and they might have Y equals, I'm not really sure on that, E to the, and now we're going to have this number we came up with, natural log of 0.5 divided by 5,730 times T. Okay, so it's a little bulky, but that's what the formula looks like. Okay, so now if you tell me, you know, how much material you're starting with and how much time's gone by, I can tell you how much is left after that amount of time. Okay, so that is the function. A naught has to be given. Okay. So that is that. Oh, I want to talk about that number a little bit. Okay, so when you put that in a calculator, and it is just a number you can put on your calculator, you get approximately negative 0.0001 12097, something like that. So you could write that in scientific notation, and it would be negative 1.2097. This is accurate to 4 decimal places, times 10 to the negative 4. Okay, so that's how the scientific notation's working. You're going 4 places, 1, 2, 3, 4 to the left, and so that's why you get the negative 4. Notice that it is a negative number, so this is k that we were finding. This was k, the constant. And we were expecting it to be negative because it's a decay model. So we're getting less of the amount, not more, and that's why k is negative. But, and you can write it that way, but usually in the formulas that I see, they don't. They just write k for carbon-14 as negative 0.00121. They usually just go 3 decimal places and they use that number. They don't put it, oops, I left out a 0, didn't I? 0.000121. And they don't put the scientific notation because they're going to put it in a calculator, and you could do that on a calculator still, but I'm just writing it a little better. But just the formulas that I've seen, they usually just put that in for k. All right, and so what was the answer? Well, our answer came from up here. That was a function of time. We do have to know, though, how much we started with.